So this is just going to be pretty much a practice run so that we can get an idea of how these will work, I suppose. Yeah? Yeah, so I put this presentation together yesterday and I spent most of the time doing the pictures. So that's why...
They're cool pictures.
Yeah, I'm pretty happy with them. So, and it'll serve well for trying to do the presentation that you have in, so there's templates all here and ready. So that's good. So these lunchtime seminars, I don't know what our big dreams for them, but I see them as just being able to chat to each other and identify things that you do, maybe find things that we both like. I don't know. Why did you want to do them? These seminars. Yeah. I think it's because you want it to feel like there's a maths culture here. Yeah. So, because all serious universities would have something like this, and so we should as well. Yeah. Is our idea. Yeah. And I don't know about, maybe recording them or making them available to people. I don't know whether there would really be much interest in that and could cause a lot of problems, but see. Eventually, like if we have enough kind of, I think if we get a flow of them just happening, then they can be the sort of thing that people can attend, which is why I'm happy to go through this today, even with no one here. And so our schedule, Tim, September 1st?
Yeah, I did send the title, but maybe didn't get to you. Pursuit, evasion, and multi-objective mark-off decision processes.
Yeah, sounds good. And Sudarshan, did he agree to August 18th, Vicky, or did you just tell him he was doing it? I think he said no.
He didn't disagree. He hasn't run away screaming yet.
Lynn said that she'll do a talk, cool. And Gleb will do a talk. And yeah, the way I see them is not for them not to be research talks, but them to be related to research. So, although, having said that, I realized when I just said, I'll just do ranks aggregation, that then I had to think up a talk, whereas it would have been much easier to be able to recycle a previous talk that I given. So
but this will be more interesting.
I don't know. Maybe. Okay. So here's the idea. Here's some of my pictures. So when we want to make a decision, so we have multiple things that we want to make a decision about. So we have 4 movies and 4 people deciding what movie they want to see. One of the most straightforward ways of being able to do this is everyone submits like a score, of interest, and then the best movie or the one that they're going to all decide to see is the one that has the best output. The problem with these kind of models, even though they're very good and deterministic, is that once you introduce any kind of scale, then you leave that liable to being vulnerable to people submitting insincere ratings. So the last girl here says, no, I really don't want to see Ex Machina, or I don't want it to be the winner, and so I'm going to give it a 0, even though it's clearly not going to be a 0 film, and then submit. And so she's able to upset those rankings and actually make this third, the movie that's ranked 3rd by every single person, she's able to submit an extremely high score for and come out on top, and then able to make Chappie 2nd and like this. So one of the key things that can mitigate this is just you don't take into account those scales, because everyone will have a different rating scale anyway, and so it's maybe what you're more interested in, the preference. So this is done in job employment opportunities. It's done in student evaluation, where people just submit rankings, their preferred rankings. But even rankings, depending on how you put them together, still are able to have this problem. So again, all these 3 people have this movie ranked as their top one, but then the last person is able to say, no, I'll rank it last, because then the movie that I want to win, or a movie that I want to win, and able to get it so that actually pulls down this movie down to 2nd, as this one comes to 1st. So it's liable, it's susceptible to those kind of attacks as well. But there are a whole lot of other ways that we can aggregate this kind of information. So this problem for me is, nothing I something I never formally studied, but then comes up all the time because you have in machine learning tasks you often have to combine the outcomes of different methods. Sometimes they're not commensurable, so scores in one not necessarily transferable to scores in another, so all you really have to go on is the winner in each case, or the ranking in terms of their performance in each case, and so combining them in a reliable way. So it's got a very rich history, this idea, mainly from social choice. So obviously voting in elections is one of the most important things that we have to deal with these days. And so it's been studied in that context, but then has been studied, because it's the same problem that occurs again in other areas. And the appeal and the reason why it's still, the reason why it's still studied is essentially because you do have lots of situations where you don't have this absolute information, or where there's some uncertainty about that information, and the most reliable thing you have is a linear ordering over alternatives. You do always, if you have independent sources or unrelated sources, then you have this problem that their scales can be incommensurable. And one of the things that we've seen with some of these techniques is it can mitigate the vulnerability to those attacks where people give an extreme score, but not completely. So some formal mathematics of it, just to make this seem more like a maths talk. Different notations can be used. So one way that you can think of aggregating ranks is you encode them into a ranking. So if you have multiple objects, you assign for each object, so the ith input, you give it its rank. So the example here is if we have 4 alternatives and they're ranked this way, so the third one's the best one, fourth one's the second best, the corresponding scores have their ranks here. So because the third one's the best, it has a rank 1 here. Because the fourth one's the second best, it has a rank 2, rank 3, etc. So there's like a direct kind of mapping from an ordering like this into a ranking system here. You can have tied ranks. Whenever you do this, what you usually do is add up the ranks and divide by the number of ties. So if you have first and second, so if third and alternative 3 and 4 were tied, then they would each have a rank of 1.5. That's the way you would usually do that. But we can also think of it as in terms of a partial order, or what you usually want actually is a total order. So in this case, you've essentially got a relation. It's reflexive, antisymmetric, and transitive. So where a pair is in the relation if one alternative is ranked above another. So if A is ranked above another, then we say it's in the relation. So sometimes it's easier to work in this space as well. And obviously, as long as you've got a complete order and everything's ranked, then there'll be a one-to-one mapping between these partial orders and the ranking systems. Okay, I think that's about as much. Oh yeah, and then you can say their functions like this. So just a mapping based on the number of, so your input space is like sets of rankings, and then your output space is usually a ranking. Sometimes you might just want partial rankings, so you might just want a first, second, and third from everyone, and then you want to aggregate that into a first, second, and third, even though you might have 100 alternatives to choose from. So in the Australian elections recently, I think we just had to submit 6 or something. Yep. Okay. So, different things. By the way, if anyone has any questions, feel free to stop me at any point. The Borda count is probably one of the most classic ways of dealing with rankings. It's very straightforward. It's basically you give every place a score, and usually the traditional way is that the score corresponds to how many alternatives it outranks. So if you have 5 alternatives, then first place will get 4 points, etc. But you can have other systems as well. And then so you induce your ranking then just by summing the ranks, or because in my case, you need to reorder them, etc. So it's very straightforward, very easy, and nicely deterministic. So as long as you've got enough inputs and enough decision makers, then you're unlikely to get tied orderings. So you usually should be able to determine a winner. in this case. Problem with the Borda Count, which is similar to problem in absolute ratings, is it's very susceptible to the method you give. So for instance, in the NBA, Defensive Player of the Year has essentially a Borda Count approach. They have something like 300 or 200 sportscasters and experts who each give 3 votes, first, second and third place for Defensive Player of the Year. First place gets 5 points, second place gets 3 points, and first place gets 1 point. So 2 years ago, it was kind of controversial because this was the first place rankings. So the top guy, Draymond Green, had a pretty clear preference for the top position. Kawhi Leonard for the second position, but then Kawhi Leonard had a whole lot more second place votes. So they got 5 points each for the top position, 3 points each for the second position, and then for the first position. So Kawhi Leonard ended up winning, and people were like, why did he win? It was Draymond Green who was like preferred as the best player of the year. And so you get these kind of, you get things where people can argue that maybe that outcome isn't the right outcome. So this often happens with Borda Count. And one of the big trip-ups of Borda Count is that if you assign just a different scoring, so if we instead said 9, 3, and 1, then we would have it the other way around. Wait, I think I've got those outputs are the wrong way around. Yeah, sorry. Sorry, if you actually do 9, 3, 1, this is the other way around.
So is that suggesting that you can actually tailor the outcome you want just by appropriate choice of points?
Yes. Yeah, and that's pretty much the proof. So with essentially that you can have any alternative, up to other than if you've got dominance, someone winning all of the places. Yes. If you have 3 alternatives and they've got a mix, then you can, if you just scale the points up and down, you can make anyone the winner. So it's one of the problems. Still, it is a nice simple way to do it. And so in machine learning, if they have classifier combination, often the Borda Count is the simplest way, because as you'll see, there are other methods to explore much more complicated. But it's not, so it's one that hasn't, I don't think anywhere. I think they used to use it in old kingdoms and stuff, but I think everywhere else, voting systems usually don't use this kind of aggregation.
Is there a method to get 9, 3, and 1, or do you just...
I just fiddled with it, just until I got it.
Yeah. But then
well, I think 7, 3, and 1 works actually. As well.
I'll give you an example because I'm involved in an organisation at the moment that has a season of events, and you get a certain number of points for first. It's like Formula 1, but it's not. And they're debating how they're going to resolve the end. We've been awarding these points, but is this the fairest way? Should we use trimmed means or something similar across people, and then doing that? But clearly there are people arguing for a certain result. So one of them is the parent of one of the competitors, who's clearly arguing for a result that's going to cause his son to win.
If you have that information there first,
Exactly. So it would be. It seems like the sort of thing where you need to agree on the scheme up front.
Yeah, and I think as long as you agree on the scheme up front, then it becomes fair. And, if these are often, if you have too much weight for the first position, then the second, you can set it so that a second position basically becomes redundant, and so it just becomes a plurality voting anyway. So in preferential voting, they often have more sophisticated schemes. So in Australia, we have this situation where we take out the lowest winner and then add their scores. So this is what the seat of Melbourne looked like with first place votes. But then because of the general flow of preferences, so Labor usually would have their second preference for Greens. So once they're taken out, their preferences go to Greens, and so Greens end up becoming the winner. But you have the problem with this kind of situation. So this situation is usually good because it means that if anyone actually has a more than 50% majority with every other candidate in a 2-person contest, then that person will win. But the problem is your set of preferences don't necessarily guarantee that you'll have that situation. So no one might have that kind of win, and then these things are happening. But odd things can happen here because so Liberals probably would less like to work with the Greens.
Mm.
And so if they actually have less of the vote, then they get a better outcome for themselves. So they get Labor winning if they have less.
Oh, that's
So,
funny.
and this, often happens. So
Yeah.
they often approach this from, okay?
Yeah.
Gotcha. So often this is approached from they say a game theory ends up being a game theory perspective, or even
Wow.
situation like this, Greens can have even all of the, the Greens getting more of the preferences even ends up being worse for them. So it can have kind of those funny things that happen, depending on the way the flows. There's some results saying that if your candidates are on a spectrum and everyone votes in preferences based on who's closest to them, then you should always get consistent results. But because, there's often cycles and things like that. So I have all of these nice properties. So these are the famous ones that Arrow proved these are not compatible. So if you have a preferential voting system where you have to have, if everyone votes the same, then that's the outcome. There can be no single voter whose preferences are always satisfied, so non-dictatorship. The problem is usually this independence of irrelevant alternatives, which is in the cases before, if you take out someone that wasn't going to win, so in this case here, since Greens win, if you actually take out one of the competitors, then it shouldn't affect the outcome, but clearly it does. So it's usually the problem in any voting system, and not many of them, other than things like where there's a strong dictatorship or where you're only taking into account first place or things like that. But there's some other interesting rules. So non-imposition, so you have to have a voting system where everything is possible. The Condorcet criterion, so this is what I was talking, Condorcet. Sounds like, it looks like Condorcet.
I don't know.
Anyway, so these have, so that's the thing that I was talking about before. So a Condorcet winner is someone who would, if there's a candidate or an alternative that would beat every other candidate in a two-person race, then they should be elected the winner by the system. So a method that is a Condorcet method has these properties as well. So non-imposition, that fulfillment, and then the majority criterion. There's some other ones, so Pareto efficiency. Monotonicity is the idea that if an alternative increases its level of preference, then it doesn't decrease its ranking. So that was an example that happens before. And another interesting one, which I only found about yesterday, Smith criterion, is that you always have, if there's a set of votes that are ranked completely above another set of votes, so you can partition the set like this, then the winner should be someone from the Smith set, so in that upper group. The thing I was talking about at the start, in the initial example, is referred to as invulnerability to burying or compromising, which is the idea of someone can submit an insincere ranking to get a better outcome for themselves. So, basically someone can vote against their actual preferences to get their preferences, is this idea. And this is something that comes up not just in these systems, but in sort of talk recently on argumentation. Even when you have just logical, a question, I don't know, I think it was an example in law where you're just arguing whether something happened or not, and it's just basically a yes-no vote. You can still have these things where you want the outcome yes, and you actually vote no in order to get the outcome yes. So, those kind of things. I think they're very interesting. Yeah, all of these things. And the thing is that, most systems can't satisfy a good number of these rules. And that's why it's still an interesting problem, because we have all of these things. So one way to look at it, so rather than just coming up a rule based on these properties, you can think of it as an optimization problem where you're minimizing a distance. So this is what we usually have done. So we look at, we have a penalty. So this is for a penalty over real functions. In the context of voting systems, a penalty function is basically one such that if everyone votes the same, then you've got 0 penalty for the outcome. So the outcome's the same as what everyone voted, and you say that there's unanimous vote, no penalty, or no error in your outcome. And then the other condition is basically one that you want to guarantee that if you do have penalties which are equally likely that they are in some way adjacent to each other. So if you have penalties for real numbers, then you want that to be a convex set. With penalties over rankings, what you want is to have rankings that in terms of the penalty or distance function that you use, they should be close to each other. Is what you probably should have to make something distance. And so a normal distance has the properties of just being non-negative, reaching a value of 0 when two things coincide, and then this triangular inequality. But a lot of distances in rankings, so you can make distances like this. So based on your rankings, you can just use this Minkowski distance, change the value of Q. So if Q is above 1, then we get a distance. But this, when you have rankings, because a ranking doesn't just go up from 3 to 4, the 4 has to drop to 3. So you have, you don't have the whole set. You've kind of got a lattice. Some things that would traditionally be expected to be distances aren't. So Spearman's row is this kind of form. So it just calculates the squared difference between ranks and then does this normalization, but it's not technically a distance because it doesn't satisfy triangular inequality. So you could do something like Spearman's. So I think it's pretty much the go-to thing for evaluating whether two rankings are similar, but it's not used as much in terms of aggregating rankings, I think. One distance that I think is probably the nicest is called Kemeny distance, and this basically counts the pairwise agreement. So if you have two rankings like this, so 1, 2, 3, 4, 1, 2, 3, 4, you see they do agree that blue is above orange. They do agree that blue is above green. They disagree about blue and red. They disagree about red and green, orange and green, and they disagree about green, orange and red. So you could have some kind of normalization, and then the distance would be like a third or something like that. So these methods, I think, in decision making and in aggregating ranks are probably the most promising. And if you have a method that minimizes this penalty, then it does satisfy that Condorcet criterion. So you should have a winner that if they outrank everyone else, then overall then they should win. But there are other distances as well, so we can use cosine. Okay, so I might see if I can zoom in here. Oh, it's me. So distances in this way can be thought of as acting over a lattice with distance or some kind of topology. So in this case, so we're looking at the difference between an A, B, C, and then a weak A and B and C are tied, and then A, C, B. So each of the steps is like basically swapping a pair of alternatives. So this is the topology of the, what was it? The Kemeny distance. Kemeny distance? Yeah. So this is topology of a Kemeny distance. So ABC is one step away from A, B, C here. But this is 2 steps away from here, because if you look at the ranks here, it agrees that B is above C and it agrees that A is above C, whereas here you don't have those two. So it misses out on 2 agreements when you just swap from here to here. So it has the double lines represents a distance of 2, whereas here to here, they both agree that A and B are above C, but they don't agree about A being above B. So it's one disagreement. So this is Kameni distance. So you can imagine if you have multiple voters and they're say here and say here and maybe here, then you would be looking for which out of probably in this area minimizes their difference. Probably, and it would probably be one of these. Yeah, one of these three. On the other hand, this is what you get if you have a Manhattan distance. So if you just calculate basic distance between the ranks. So in this case, you have a shorter distance between ABC and all pairs equally rated. So this only differs by 2 to here, differs by 1 to here. So does satisfy triangular inequality. So if we get from here to here, it's quicker to get straight across here. This is a distance that was proposed in another thing where it just, looks at this topology and says, okay, if there's only one swap that could be different, then that's just a distance of 1. So it's basically same as Kameni distance, but it doesn't have those double swaps when you go to a neutral thing. But this one had some problems. So I think if you aggregate things using this way, I think it doesn't satisfy triangular inequality. And so you get, again, some misleading things. Okay, what time? How long have I been talking for? Too long? Very long. Okay. Okay. Well, yeah, I think I don't have much else to say. So yeah, often our methods look at penalty minimization. So the traditional way, if you're going to choose an output, is you take all of your sets of rankings and then you want to, find so that from each person to this overall ranking, you want to minimize that distance. An interesting thing that I heard talked about at the conference that I was at a couple of weeks ago is rather than calculating this distance, they said, how about you just calculate the distance until you get a Condorcet winner? So in that case, with this set of things, or the minimum change you would have to make is just this swap here, and then once you have that swap, you get the blue beating red a majority of times, and everyone else. So beats here, beats here, beats here. So that was the only swap that was required until you all of a sudden get a Condorcet winner. So I kind of found that an interesting but dubious idea. But either way, whether you have that or not, the big problem with this is when you're doing penalty optimization over this space means you've got to look at all of these orders. And so if you take into account weak orders, as soon as you even have 7 alternatives, then you're up into 50,000 different possible orders. So it's the main problem, and it's why things like Borda Count or other kind of approximate methods, so even the Kameni distance can be approximated pretty well with a Borda Count-like approach. So often in machine learning tasks, when people want to do this, they might do an approximation at least to limit the number. So maybe you just limit it until you only have 5 alternatives using a Borda Count approach, and then you can do the optimization within that kind of space. Okay, that's it, I think. Thanks. Yeah. Yes. Yeah. So is that what you expect? Was that all you hoped for, Vicky? Because this is your dream coming to life. You like my pictures? Yeah, green they are. Yeah. Good.
So what do you think is the answer for issues like our preferential-based voting system, which clearly has anomalies that people get very unhappy about?
Yeah.
You get circumstances where one party has twice as many primary votes as the next person, but still loses.
Yeah. The problem is usually that the time and effort. So I think like some good systems are usually where you just probably what you should do is you run it like a basketball competition, and you have every pair get everyone to vote on every pair, and then do something like that. But then they do systems like that they do like in France, and they drop out a candidate at a time.
Yeah,
They have
yes.
multiple rounds.
Yeah, multiple ways.
But they don't like that because people don't vote seriously on the first
No, of course
few
not.
voting.
No, they
So
vote.
it's even
They
like
vote to drive people out of the election.
Yeah.
Yeah.
And so even on like the Brexit vote, you don't have people vote. So I mean, yeah, like your big problem is when you have these situations where people are unfaithful in providing their opinions.
So one of the things I thought about, given things we've talked about in the past and things this whole recent election, is what is the actual effect of people who vote in unusual ways? In other words, we run and this is because we saw so many of the predictions on election night came out to be wrong.
Yeah.
The predictions are based on a two-party preferred. In other words, go on last election, who were the two top candidates?
Yeah.
Hence, we're going to assume that that's the voting system until we prove otherwise,
Yeah.
and we'll distribute preferences and predict on that way.
Yeah.
And I'm wondering about, in something where you have a seat with 10 or 12 candidates, and some of them are from very esoteric parties, they might get 0.1% of the vote or 1% of the vote. What's the effects on the whole system based on their preferences? So, for example, let's say I'm a person that wants to vote for the Pirate Party and the Sex Party and the Sunday Party, and I put Liberal and Labor last, how will my vote count in the end, and how will it affect prediction in the short term?
Yeah.
And that's I think that's an interesting question.
Because those ones often wouldn't be, because they only keep on taking that bottom person off until they get a majority. So if you're Liberal and Labor way down the bottom.
But I'm wondering about, if you have lots of people like that, or, if you have the old system where most people, probably 80 to 90% of people voted for the two parties, then things are probably quite predictable. But I'm wondering about what happens when that proportion of indiscriminate voters, people who will just vote stupidly or whatever else, can they actually affect who's dropped off first? If they represent a significant proportion of the pool, can they actually drive a candidate that would otherwise maybe still be in the run later on? Can they drop them out in an early round because too much votes distributed away from that person initially?
Yeah.
I don't know.
Yeah. Well, because they would have to be not receiving much of the, they would have to be never be high. Yeah. So you would have to have so many people that put them. And so so if you're saying if everyone, if you essentially get like at Smith's set and everyone actually puts the ridiculous then they should win. But I think there is essentially even the idea that we have such thin majorities for such important decisions.
Yes. So my biggest concern in this election as well, and some others, is that when there's clearly someone with a very significant first preference vote, they're getting 48% of the first preference vote. They don't actually have the 50% first preference, so they don't get the declared winner straight away. But then second preferences come in, and it's all the preference deals that have been done. So the people know, based on history, this candidate's going to get about 45% of the vote. So actually our second preference deal we deal with is what's going to determine the election. Yeah. And most people who go to vote don't understand how the preferencing system works. And so they just go, well, I want this person first, and if I can't have them, I'll have this person, not understanding how it's actually going to affect the vote.
Yeah. Because, I think that's the problem as well. That, essentially, if like with this Labour and Greens thing, or, you would, you have, it does become a game theory this thing of you're saying, okay, I'm predicting that they're going to get this amount, so therefore I'm making a deal with these people.
Yes.
And
that's actually how most of the election plays out. Yeah. It's the backroom deals. It's actually not based on what people vote. It's based on the backroom deals, based on statistics of how people vote.
With this one, you couldn't just do a 1 anymore. You had to actually fill.
No, that was the 11. That was the with the upper house it was 6. You have to do 6 or
12. Yeah. 6 or 12.
And 6 above or 12 below, or you could still do all.
Oh, could you still do all?
You can do all. You can always do all.
I didn't.
They just take the 12. They just take the 12. You're always allowed to fill in the entire ballot paper, but they'll only count a set number. But in the lower house, you have to lumber them all. Yeah. You used to be able to do a 1, and then that took the preference deal.
So they eliminated that. But then you still get your, the
people
party
still
that
vote on
you're going
party lines,
for.
And most people still vote on party lines. So, and then it goes on to the deals. So,
but in the Senate though, they just get the percentage rate.
Oh, it's